Okay, so, welcome to everyone to the conference Curves over Finite Fields, Past, Present, and Future. Welcome to the one who are now attending right now, and to the one we will see it a bit later when it's daytime for them. So as you know, one purpose of the conference was to celebrate the release of Serre's book on the topic, and also to summarize the main progress since 1985. Of course, we could not be exhaustive, and so we will definitely appreciate if you give us your perspectives. It's a community thing, this conference, so give us your perspective, your comments, your references, everything you think we should have talked about in the Zulip chat. And in this way, we hope that we can get a complete panorama for the community. But research is also about the future. And as you can see, the second part of each plenary speaker's talk is about sharing some open questions and possible developments. And also, as in the past, the topic will definitely benefit from ideas from other areas. And that's why we included a few talks which are not directly related to curves over finite fields. So maybe, we can get some new ideas for the future from there. Well, it's an online conference and it was not planned like this from the beginning. It should have taken place in a beautiful location in the Spanish Pyrenees. We are of course sad we could not meet in person and enjoy the mountains. But this change of format is also the opportunity to have everybody being able to exchange equally. We have more than 250 participants registered, and many young ones, which is great, as they will be in charge of preparing the future of the field. So we are really happy, and we are really glad to see them also on to know what they are about to do. I'm just going to conclude with a few words on how we shall proceed during the talks. So as you know, and as you see, the talks are going to be recorded, as many of you won't be able to attend right now for time zone, personal or professional reasons. The link to the video is going to be displayed on Zulip more or less 1 hour after each talk, so you will be able to find it there. As I said, Zulip is also the place where you can continue your exchanges with the speakers or with other participants after the talks. During the talk, if you want to speak, please raise your hand. So there is a small button at the bottom of the screen in the reaction icon where you can raise your hand, or you can write it directly in the chat. And the chairperson, so for this first talk, it will be Hugues, is going to see your question and give you the floor. If possible, when you speak, and if it's not already the case, please turn on your camera, and that will be great. In case of turbulences during the talk, our aircraft has one rescue Zoom link. So, it is in the announcement stream on Zulip. In case of trouble of connection on your side, then please just write to one of the organizers and we will try to help as we can. Okay, that's all for me. Well, enjoy the conference, and Hugues, that's for you now.
Okay, thanks a lot, Christophe, for this introduction. And thanks to all the organizers for preparing this conference and for making it possible. So our first talk will be by Alain Couvreur from INRIA, Saclay, and École Polytechnique, Paris. And he will speak about algebraic geometry code. So as Christophe recalled, you can ask questions in the chat. And okay, that's all. So maybe Alain, you can start.
Okay, so before starting speaking, we'll ask if everyone hears me correctly, because I can still make some improvement, and I start sharing my slides. So now you should see my slides, and it's going to be better. So, okay, so as both Christophe and Hugues said, feel free to interrupt me and ask questions. So it's always more pleasant to have some interaction during talks, and even more when we are online. Yeah.
We do not see your slides. We see your LaTeX source.
It's not my LaTeX. Oh, yes, it's my LaTeX source. Sorry about that. I try again. Okay. Yes, that one should be better. I'm sure you appreciate how clean was my LaTeX sources, but let's have some more friendly environment. Okay, so thanks a lot for. First, I need to thank Christophe and Elisa and all the organizers for to have made this conference possible, even despite the pandemics. And I'm very honored to be one of the speakers, and actually the first person who speaks to this conference dedicated to celebrating the publication of Serre's book on the topic. So as probably a lot of people who know me, my topic is codes, error correcting codes, and in particular algebraic geometry codes. And it's not directly an area in which Jean-Pierre Serre worked personally, but it is clear that his work, his contributions, and many other contributions from the community of number theory and algebraic geometry strongly impacted coding theory. And it is kind of reasonable to say that, yes, in the last 40 years, and in particular after the appearance of the works of Ihara and Strassman, Vladutz, and Think, our vision of coding theory completely changed. And okay, so this is more or less this story that I will try to explain, to recall today. And as Christophe said, so in tomorrow's talk, it will be more focused on, let's say modern developments and open questions from coding theory, from practical application, which feed arithmetic and algebraic geometry from new question and new elegant problems. Okay, so this is the outline of my talk. And basically, I have in mind that today I will mostly give some recalls about coding theory, and then explain the story apart, not the whole story of algebraic geometry coding theory. It will be rather long to explain everything, but a part. And tomorrow's talk will be dedicated to, new issues, open questions. So I'm not completely sure on the way I will organize that. So maybe I will start to speak about new issues today if I have time, but at least the two first parts today. Okay, so let's start with coding theory. So as you know, coding theory starts with persons, and if we have to cite two names, probably we should cite Claude Shannon on the one side and Richard Hamming on the other side. So Claude Shannon is extremely famous for his 1949 paper in which he explained what information theory could be and provides probabilistic models permitting to estimate what could be the optimal in terms of source compression, but also in terms of error correction over a given channel. So it's theoretic, non-constructive, but it's the basis of what can be done, what cannot be done. On the other hand, we have Richard Hamming. So Richard Hamming was an engineer working at Bell Labs, and he was on the beginning interested in elasticity theory, and he wanted to make calculations, and he developed machines to make computation, and was kind of upset to launch computation for whole nights, and discovers that at some moment there was one error which completely killed his calculus and his computation. And his observation was, it's possible, if you have sequences of bits, to add a parity bit, just the sum, the binary sum of all the bits, just to check whether the computation is still okay. And his idea was, okay, if the computer can check whether there is an error or not, maybe it can correct it and don't have to wait that I come to correct it manually. This reflection led to a first code, which is the famous Hamming code, so a code of length 7, which corrects one error, and that he personally implemented. Okay, so that's for story. With that story, error correcting codes have had numerous applications, and let's just mention a few of them. But as you may know, in the late 60s, we sent so the Mariner program. No, it's not in the 60s. The Mariner program was a program to send spacecraft to observe the dark side of the moon, and the pictures have been sent by satellite. And in that spacecraft, you see that there was the implementation of Reed-Muller code, so a code obtained by evaluation of functions in Boolean functions in 5 variables, which was implemented. And actually here you have pictures sent by Mariner 9. And actually, yes, NASA engineers were really impressed by the quality of the picture, which is, of course, a technological success, but also a success of mathematics, because they did not expect to have such good pictures, and that's error correcting code would permit that. In terms of wire telecommunications, so here, since I'm French, I need to show our French pride, which completely disappeared because actually France invented some kind of web before, well, in parallel of the web. It was Minitel, and I think every French person at some moment has it in its apartment, close to his phone, Minitel, which permitted him to, in something, to surf on specifically a French web. And in that French Minitel, there was implemented a BCH code here with these parameters. So I will recall what we mean about parameters quickly after. And another famous application is CDs and DVDs, and it's always funny when I started to make some vulgarization talks. I spoke about CDs, and at some moment people told me, but you know, if you speak about CDs to high school pupils, in a few years they will no longer know what it is. And I think we are now in this situation. But so it's part of our history, but the quality of the sound in the CD you heard when you were younger was due to the quality of an excellent code, so a Reed-Solomon code, actually a pair of Reed-Solomon codes which were interleaved in some manner. Okay, so that's for late history, and let's move to other applications. So here, no more pictures, but it's an important fact that when we speak about error correcting codes, we always think about communication and storage. But actually, the impact of coding theory is the practical impact of coding theory. It's much broader than only communication and storage. Actually, error correcting codes appear in so many branches of theoretical computer science and in so many practical applications. So here I could mention secret key cryptography. So some invariants called branch numbers in block ciphers can be interpreted in terms of code invariants. Also, some attacks called correlation attacks can be meant in terms of decoding of some codes. In public key cryptography, it's now known since about 40 years that using error correcting code, it's possible to design encryption schemes and also digital signatures, which are supposed to resist to the quantum computer. So a feature which is not satisfied by RSA or any discrete log-based encryption schemes. In another recent application domain, one can think about cloud storage. So we are more and more externalizing data, and we do not matter about where are these data, but they are stored somewhere in data centers distributed over thousands of servers. And we want just, our only concern is, I want to access this data anyway, at any moment, whenever I want. And this should be done. But data is stored on servers, and we cannot avoid that some server will fail, should be rebooted. And the solution for you when you use a cloud, your Google Drive or iCloud or anything you want, is that actually your data is encoded, so that if you want to access to part of data which is on a server who just failed, then actually the data has been reconstructed somewhere else and you can access it. And this is just due to coding theory. Coding theory is also fundamental in what is called secure multi-party computation. So it's another paradigm of cryptography in which you do not want to resist to an attacker. You just have personal data, and you are users all having personal data that they want to keep private, but they want to have general information on the world data. Imagine medical database, you want to preserve the secret of an individual, but you want to make general statistics. And for that, there is this paradigm called secure multi-party computation, which dates back to the 80s. And in this area also, coding theory has a strong impact. And of course, this list is far from being exhaustive. Okay, and last but not least, I spoke about applications, but it's also math. It's a very rich mathematical theory involving probabilities, information theory, combinatorics, algebra, number theory, algebraic geometry, and this is what makes coding theory so cool, and the reason why people who don't do coding theory are jealous from people who do, of course. Okay, so I told you about code just quickly. Maybe it's better. So just recall, what's a code? So what I will call a code is just a vector subspace of some space fq to the n. And what is important is that it's a vector space endowed with some metric. And actually, it's the metric which makes the theory rich. It's not only undergraduate linear algebra. So you can see, so I will speak about length. So it's just this n, so dimension of the ambient space, dimension of the code, so dimension of the code as a space, and minimum distance. And by minimum distance, I speak about these quantities, so the minimum numbers of coordinates I need to change in a word in order to move to another word. And this is what quantifies, in some sense, the way to our ability to correct errors. Okay, and sometimes I will speak about this triple. And so if I backtrack here, my Minitel used a code of length 127, coming from probably from a field of size 128. Dimension 120 and minimum distance 3. And with this minimum distance 3, was able to correct up to one error, basically. Here, Mariner 9 where the code had minimum distance 16. Here, the idea is that the spacecraft was far. We do not expect, if we have some rotten picture, to ask again the spacecraft to resend it. And so we wanted to be able to correct a lot of errors, 7 here. Okay. So now, what about how to construct codes? And the first, not the first, but using algebra, and here we are all algebraists, the historical construction and more famous one is Reed-Solomon code, which is obtained by this way. So I take space of polynomials of bounded degree. Polynomial is encoded as follows. So I just evaluate a function, so a polynomial at n values. And so n is strictly larger than k. And so if I take k out of n values by Lagrange interpolation, I can find f. But n is strictly larger than k, so I have redundancy. And here is my redundancy. And if I want to speak about error correction can be interpreted in terms of some Lagrange interpolation, but with errors, and Lagrange interpolation with errors is something we can do. These codes are known to have optimal parameters with respect to a bound called singleton bound. As I said, they benefit from efficient decoding algorithms. So that work started with Berlekamp work in the late 60s. And notice that the well-known Berlekamp algorithm to factorize polynomials has been designed in this period, while Berlekamp's objective was decoding and not directly to factorize. So another impact of coding theoretical problem, which leads to very useful objects far from coding theoretic applications. What we do not like on these codes is that you evaluate polynomials at n values and distinct values of a field, and that field it has size q, and so the length cannot exceed q. Actually, if you want to at some point at infinity, you can go up to q plus 1, but not further. And this is the moment where algebraic geometry enters in the game. So from that construction, so you can think about evaluating points on the line and on the affine line, and you can just change your affine line into a curve. And this is Gopal's constructions dating back to 1981. It's just evaluating functions from a Riemann-Roch space at some rational points on a curve. And you know that on a curve, you are no longer constrained by the number of rational points. A well-chosen curve can have an arbitrary large number of rational points. I spoke about these parameters. So Riemann-Roch permits to estimate, to give lower bound for the dimension, and minimum distance can be obtained just by observing that if you have a function in a Riemann-Roch space, its number of zeros cannot exceed the degree of the divisor providing the Riemann-Roch space. So maximum number of zero of such a function f is degree of g, and so minimum distance, which is the minimum number of non-zero, will be the complement of that maximum number. Okay. So now, how good are these parameters? The point is that there is a well-known, I already mentioned it, but there is a well-known bound called singleton bound in coding theory, which says that the sum of dimension and minimum distance is always bounded by n plus 1. And actually, if I take those two inequalities and I sum them up, then I kill that degree of g, and I give a lower bound, which tells me that we are at g, where g is the genus of the curve, from the optimum. Okay, so now just I open a parenthesis, because so we know now that we can be at g from the optimum. We could say, okay, so g should be as small as possible. So g equals to 0 corresponds to Reed-Solomon code and provides us an equality. So the codes are optimal, but we see again that g is also a parameter which permits to modulate the length, because if you want to have a large n, we need to have a large number of rational points, and this is guaranteed by a large genus. Okay, so now question, if I want to have very long code, so a very large n, how g, so g should be very large too, and what kind of asymptotic optimum can I get? So here, just forget curves a bit and just recall some results from coding theory, so some theoretical result, and just maybe you don't have to check any definitions. In particular, I didn't define the query entropy. So there is some function called query entropy, and what we can say that there exists if you fix some minimum distance of not exactly minimum distance, but ratio, minimum distance and n. If you fix such a ratio below some bound, just technical detail, then you can get a sequence of code whose rate, so the ratio dimension out of length, is strictly positive. So it means if you fix some linear growth of the minimum distance, then there is a sequence of code which permits also a linear growth of the dimension, linear in the code length. But better than that, we get some threshold. So for a fixed delta, we get some asymptotic reachable rate, but actually it's what happens typically. That is, so here I just switch, I fix the rate. You can also do that, fix the rate, and gate give some asymptotic delta, some asymptotic behavior of the minimum distance. And if you fix for a fixed rate, actually, if you take a random code, the minimum distance is always in the same range. And just a picture. So here you have the bound. So for in green, it's for q equals to 2, and in purple, it's for q equals to 49. The 49 will be useful for very soon after. And what Gilbert Varshamov says is that at least we know that it's possible to reach any point on the green curve for binary code and any point of the purple curve for codes over F49. That's the first thing. A second thing which I didn't mention, but it's always possible in coding theory to do less than expected. So as soon as you can reach any point on the curve, you can reach any point below the curve. But the important thing is that the typical behavior, so random code, are on the curve and not below. The typical behavior of a random code is good, and for a long time we thought it was optimal. For a long time we thought it was not possible to do better than random codes. Note that for q equals to 2, it's still an open question. Is it possible to do better than the green curve? And nobody knows. But for the purple curve, now we know the answer is no. And so you know that story probably, but as I said, we have this lower bound. And now if I divide by n, so I have my r, my delta, and it will be bounded by some terms depending on what we call the Hiara constant. So we have this lower bound, and Hiara constant is, what is Hiara constant? Is the asymptotic number, the following limit. So the limit of the number, the maximum number of rational point of the curve of genus G divided by G. And this quantity, maybe, sorry, probably there is some limit sub. Oh no, there is a max here, so don't remember. If the limit is not defined, just write a little sub here. I may be wrong. Okay, so I have this quantity, so Hiara constant, and using the Hiara constant and using a family of curves reaching, so a sequence of curves whose genus tends to infinity and which reaches this Hiara constant asymptotically, I can prove the existence of a family of codes satisfying this very simple formula. And the picture you probably, no, before the picture. So this leads to the question, sorry about that what A of Q can be. And we know by Drinfeld and Vladutz that A of Q is bounded by this quantity. And in the early 80s, Strassman, Vladutz, and Fink, and independently ERR, showed that using families of modular curves and Shimura curves, it's possible to reach Drinfeld valued bound when Q is a square. And this leads to the picture you all know. That is, here it's what, so in purple, the typical behavior, what happens for random code. And in green, we have a lower bound of what codes from curves and codes from modular curves can provide. So note that we can reach any point on the curve, on this green curve, because here, if you remember, here I eliminated the degree of G. And actually, the degree of G is a parameter which permits me to travel on this curve. That's the idea. So it's a set of parameters which can be reachable, and they are above, in the middle areas, they are above what random codes can do. And still, that was considered that completely unbelievable. I mean, in this area, clearly, the idea is that algebra and structured construction could beat random ones. It was really, really surprising, a very striking result. Okay, so how to get such curves? And here I will go very fast because there are other talks which will speak about that. But it's possible to get families of curves with many points. So as I mentioned, so you can consider modular curves. So in Strassman, Verditz, and Sink papers, they propose modular curves to get this optimal over fp square when p is a prime, and then over an fq square. So here it's aq square. I forgot the square. You can also reach Drinfeld values bound using Shimura curves. Later on, in 1995, Garcia and Stichtenot provided another construction, which is, let's say, theoretically much more elementary and very elegant, but requiring less technical mathematics to reach this so-called IRA bound. And I think it's maybe so, and it's still an open question. Actually, do these recursive towers are really different from modular curves? Are they the same? So it's a conjecture established by Noam Elkis. And in another direction, it's also possible to have to use Golod-Shafarevich and class field tower. And Serre gave a lower bound for A of Q, which holds for any Q, so no longer constraints of Q to be a square or a cube or anything you want. You have something which works for any Q, which is written here. So I'm not sure that this constancy, so 1 out of 96, sorry, my English, is optimal, but at least it's, yes, bounded by some constants times the logarithm of Q. Okay, so now just another question. So I mentioned curves, but it has been very early raised the following questions. Okay, we can do that from curves. It's just evaluating functions from the globals. Yes, evaluating global sections of line bundles at points. Why do we limit to curves? Actually, it's straightforwardly extendable to higher dimensional varieties. And why don't we do that? And actually, we can do. The major limitation is the mass which are behind. So how to estimate the minimum distance. For curves, we had a very trivial bound, which is given as follows. So we evaluate a function from a Riemann-Roch space. Its zeros are somewhere, and the worst case is when the zeros cover the evaluation points, where all the zeros cover the evaluation points, and this, considering this worst case, give us the minimum distance. If you looked for surfaces, you have the zeros of sections of a line bundle is a curve while you are evaluating at points, and this asymmetry makes the problem much more difficult. because you could say, okay, so I have to estimate the maximum number of rational points of curves given in curves lying in the complete linear system associated to G. But okay, they could be like this with very few rational points, but they can also split in a lot of components and then provide you code words which have much smaller weights. So, as I said, the difficulty is that we are no longer considering the degree of the divisor, but we need to estimate a number of rational points. So a strongly arithmetic problem, actually, because if you think about curves here, it's actually purely geometric. I don't need for the estimate of the minimum distance to speak about rational points. Just could consider set of points, and actually I have the fact that the zero locus of my functions are also points, and so it's just purely geometric. The lower bound n minus that degree of G is purely geometric. Here I'm moving to some arithmetic geometric problem, counting rational points on curves. Okay, so just larger focus, but as I said, for surfaces, so you have a complete linear system, you need to get the maximum number of points, of rational points, catched by an element of this linear system. And for that, we need to consider the situation where the element of the linear system splits in a lot of components. And this can be bounded by considering the Néron-Sévry group of the surface. So I forgot to write it, but I will say it. So it's an approach which has been considered by Felipe Volor and Marcos Zarzar in 2007 papers. So Felipe will correct me if I'm wrong for the date, for the year. And then you can just work component by component and then apply a veil bound or its improvement by Serre. And I really, I forgot the 2. I'm so ashamed. So yes, it's G times, there is a 2 here in the integer part. Sorry about that. Okay, or use other estimates because sometimes veil bonds are not optimal, in particular for very small Qs. Okay, so possible to consider higher dimensional varieties. Sometimes it permits to break records because sometimes if you take a curve, if you want to have a lot of rational points and you need to make something complicated, a surface typically gives you Q square points where a curve gives you Q points. So if you want to work in finite lengths over a small field, sometimes considering surfaces or higher dimensional varieties permits you more easily to break records, but at the cost of a lot of perspiration because the estimate of parameters gets harder and harder. And it's interesting to observe that in cryptography, it's also possible to do cryptography with elliptic curves and with abelian surfaces, and we can consider, yes, the discrete log problem over arbitrary abelian varieties, but it's now known that the optimum in terms of security of computation lies between genus 1 and 2. I mean, no, it's no longer relevant to consider higher genus. For codes, I could not say in terms just of getting good parameters, what's the optimum in terms of dimension, because the limitation is more on the mathematical understanding of the object. Okay, so I spoke about higher dimensional varieties, but I will go back to a less scary word and go back to curves. Okay, so I spoke about codes, and at some moment, so it's called error correcting code. So at some moment, we should ask the question, how to correct errors. So in terms of error corrections, so you start from some decoding problems. So you have a received vector, so it's a code word with perturbed with some error, so error of low weight. And here my code lies in some my code word lies in some algebraic geometry code. So here I write by calligraphic P the set of evaluation points, and here by G the corresponding divisor. So the idea is, so there are a lot of publications on on decoding, but I should say for most of them consider a very similar paradigm, which is, sorry about that, you fix an extra divisor, f. You fix it, and a part of the literature concerns the good way to choose it, but I will not consider such technical developments. So, and you will move to some linear problem, so linear algebra problem. You look for two functions, one in LF plus G and the second one in L of F, which satisfy this system of linear equations. And if you can do, and if F is well chosen, this system of linear equation has a non-zero pair of solution, a non-zero pair Q0, Q1. And as soon as you have such a pair, under some mild conditions on the parameter T, so the weight of the errors, then we know that F can be, so F, I didn't wrote F, but F is a function which permits to get, oh yes, F is a function which permits to get C back by evaluation, can be recomputed just as, yes, minus Q0 out of Q1. So as a root of a polynomial of degree 1 in with coefficients in the function field. Okay, so I will not detail the way, describe the way it works, but just one remark is that you can correct errors up to half the minimum distance, and if you want to consider a worst case, you cannot expect better than half the minimum distance, but we have some penalty, some genius penalty. And apart, so it started from this bounds, so we had so it's due to so it has been proven in two steps. So first for plane curves in 1989, and then in the general case by Skorobogatov and Vladutz in 1990. And then a lot of work to kill that terms depending on the genus. It's possible, and actually it has been done first by Erhardt and then by Feng and Rao in rather independent works. What is funny is that actually if you run this algorithm, but with a weight of error which is not genus penalty, it will almost always work. And actually here, these are works just to guarantee it works in worst case. But here it was already possible to kill the genus penalty, but with some algorithm which may fail for some entries. Okay, and then after Sudan's breakthrough in 1997, who consider what should we do if we had more than half the minimum distance in terms of errors, and he proposed to decode beyond half the minimum distance at the price that sometimes, very rarely, you will get not one solution, but a list of solutions, a short list of solutions. And here we have this sequence of work culminating with Goswami and Sudan's work, which proved that for Ritz-Solomon code, it's possible to reach an optimum called the Johnson bound, and with generalization from Ritz-Solomon codes to algebraic geometry codes. Okay. Now I have, so I'm speaking since about 40 minutes, so I will ask the chairman. So I can stop there, or finish tomorrow, or I can start discussing one modern issue on the topic. So Hugues, I'll let you know, depending on the number of questions, maybe also.
At the moment, I don't see any questions. So maybe you can start discussing one topic, and if people have questions, then they will write it in the chat.
Sure. How many time? Just 5 minutes? 10 minutes? I don't know. Christophe is so 5 or 10? 10.
Normally the talk is 45 minutes, so I mean I took 5 minutes of yours, so you still have 5 minutes, I would say.
Okay, so I will start, and it will be some kind of teasing for tomorrow's talk. Let's do that. Okay. So what did I want to speak about is, yes, actually it's kind of funny because, so I was speaking about decoding, and I will just speak again about it, and then in the last part of my tomorrow's talk, I will go back to decoding, but with another point of view. But just here, I wanted to point out that decoding can be interpreted so decoding of codes from algebraic curves can be interpreted in a very simple manners, which surprisingly permits to more or less exclude curves from the vision. So here again, I go back to the original problem. So I have my decoding problem. I have my code word obtained by evaluation with some errors. So here it should be a bold case E. And I wanted to solve a linear problem, but I didn't say, where does this linear problem come from? Actually, the original idea is we will look for a function in my extra Riemann row space L of f, which kills the error. That is, whose zeros will cover the error position. If I do that, I have this identity, which is kind of elementary, actually, because if I ask Q1 to vanish on errors, at non-error position, yi is the evaluation of f at pi, and at error position, Q1 vanishes, and so I have 0 equals to 0. So actually, this is a problem I want to solve. But what are the unknowns? There are my Q1 and my f. And here, this is a quadratic problem. I mean, if I write it with variables, I will have quadratic equations. And the idea of considering Q0, which will play the role of the product of Q1 by f, is precisely to go back to a linear problem. So it's a linearization. And linearization of multiple variable polynomial problems are possible, but it's not always work. In general, when we linearize, we get a space of solution which contain in some way the solution of our problem, but which is much too large. And so linearization is not always a solution. What makes here linearization possible is due to the fact that here we are considering the product of an element of L of f and an element of L of g, and their product is contained in a Riemann Roch space associated to f plus g. And here, what I need to emphasize is that here, the dimension of that guy is more or less linear in the dimension of those two guys. Is close to the sum of their dimension. Actually, it's the sum of their dimension plus the genus. So for small genus, actually, you have a low growth of the space of the span of all the products. And this is kind of unusual. If you take an algebra and you take two finite dimensional space in this algebra and you look at the span of all the products, you will have a dimension of the span which will be more of the order of growth of the product of the dimension, while here we have the sum. So this linear growth is the key of the efficiency of this linear process, this linearization process, which permits to have a polynomial time decoder. And what's behind is the well behavior of Riemann Roch space with respect to this span of all the products. Okay, so actually, this point of view can be made abstract, and it's possible to completely exclude curves from the point of view by considering products not at the level of the function field, but at the level of codes. And at the level of codes, so code words are obtained by multiple evaluations. So what corresponds to product on the function field will be the component-wise product for codes. So here, this very, forget that comma, this very stupid operation, the component-wise product, permits actually to provide a completely abstract description of decoding. This is what Couvreur and independently Pelican proposed in 1992. So Pelican called that the error correcting pairs algorithm, and it's a sequence of criteria that a code and some star products of code should satisfy so that we have a decoding algorithm. And this permits to describe actually, this algorithm that I did not describe in depth in terms just of star products. So I will not give the description because it's kind of rough when describing it this way, but it's possible to have a completely abstract description, and it's this point of view by Couvreur and Pelican permits to observe that if you have codes whose star product with other codes are small, that is a behavior of the star product which is more linear in the code length than quadratic, then you can correct errors. And actually, code from curves come from Riemann-Roch spaces. And for Riemann-Roch spaces, we have this behavior, so that I just described, on the span of product, which grows not very, which grows slowly. Yes, it's you can interpret that in terms of the degree of the Hilbert function, for instance, which in some sense describe this speed of growth. And code from curves permit this decoding because of the behavior of these products. Actually, it's a bad news if you want to decode codes from surfaces or higher dimensional varieties, because if you look at if you look at the span of products of two Riemann-Roch spaces on surfaces, it will not behave as nicely as for code from curves. And maybe I will stop here by a first set of questions. So this observation on star products leads to the question, what kind of codes, what kind of code family provide such small products? And this is very strongly related to some additive combinatorics problems. In additive combinatorics problem, there are several works from Knesser, Cauchy Davenport, and Freiman, who describe the behavior of subsets of groups whose set of sums are small, and this can be translated in terms of algebras. And for codes, at the level of codes, you can have some analog of Knesser theorem, which says that the dimension of the star product of two codes is bounded from below by their sum minus some terms related to some stabilizer. But you can consider that frequently this term will be 1, and this gives the so-called Cauchy Davenport inequality, which tells you that it will be lower bounded by the sum of the two codes minus 1. And this is exactly what happens if you consider codes from a curve of genus 0, so Reed-Solomon code. And more generally, if you look at additive combinatorics, Freiman consider all the subsets of groups which satisfy such an inequality, so cardinality of the sum, which is twice the cardinality minus 1 plus some penalty. And he classified all these subsets in the additive combinatorial settings, and here we are in more multiplicative combinatorics setting. And in this situation, it's completely open question from my side: is it possible to classify codes which satisfy this? And here I say with a gamma which is small, let's say gamma is in the order of the dimension of C. And more generally, yes, codes I do not consider an asymmetric situation, just codes whose square is small is an open question. We know that curves can provide them. Question, are curves the only way to provide them? Okay, and I will restart from that, but now, so Christophe gave me 5 and I took 10, so I will stop there. Thank you again.
Okay, thank you, Alain. So I don't know if we can applause with Zoom, but thank you.
You have a small icon to clap also.
Oh, yes, I cannot see that, but I appreciate it.
So now it's time, we have a little time for questions. So either you can raise your hand or you can write your question on the chat. So the organizers also can ask questions if they want. Okay, maybe I will start with one question. So I guess, do you have an idea of the motivation of Gopa when he introduced algebraic geometry code? Because so probably we did not have this certain value bound at this time, so he did not know that he could reach asymptotically good code with algebraic geometry code. So did he have specific applications in mind?
I don't know. So the paper is very short, actually. What I understood, but I could not remember who told me that, and maybe I'm wrong, is that basically, so in a former paper, so in 1970, he designed some codes described by rational fractions, and in some sense residues of rational fractions, and probably this description, which is what in particular in cryptography people call the Gopa codes. This is the reason why I prefer not speaking about Gopa codes, but by algebraic geometry codes when we consider codes on curves, because there are also, yes, Gopa codes coming from his paper of 1970. And this residue description was, he introduced it probably to have a good description, a nice algebraic description of syndromes. And so it was a good formalism to move to a decoding. And as far as I understand, at some moment, someone pointed him out that, oh, it's funny, what you do is just evaluating some residues of differential forms, and why not doing that on curves? And this is what he did. And it's kind of funny because if we think read and Solomon construction, so it's just evaluations, and now we think about algebraic geometry codes more from the point of view of evaluations, but there have been this this little trip in the world of differential forms, because they are really historically been introduced by differential forms. So I did not answer your question because you probably understood I did not have the answer. But yes, I suppose I would say maybe just he made it because he thought it was fun. And if he did, actually, it's just to prove that someone, it's a good thing to work for fun also.
Okay, thank you. So I see there is a question from Felipe. He's asking if there is so you explain the linearization part in the decoding procedure. He asks if there is also such a linearization in the list decoding algorithm of Sudan and Goswami and other people.
That's actually a very good question. It's I could say I'm tempted to say yes, but not completely directly. That is, sorry, I will just move back to. So clearly here, so the linearization consisted in choosing Q0 as to set, yes, in some sense, we set Q0 as the target from the product of Q1 by F, or minus Q1 times F. Okay, and so what Sudan proposed, I will forget Goswami Sudan, but just Sudan says, okay, so I can realize F to be the zeros of some polynomial of degree 1, and then I could generalize and try to realize F as a zero of a polynomial of larger degree. And this will permit to have a list of solutions. By this manner, I don't see directly the linearization process. One thing that I did not mention is that if you think just on the level of Fritz-Solomon codes, just with polynomials, it's going to be easier. There is some other version of list decoding, which is called power decoding, which consists in starting from this decoding problem and then doing star product. You do the star product of y by itself. You get star product of c by itself plus terms, depending on the error, and which actually are non-zero at the same places of the errors. And you start from one decoding problem, you get several decoding problems by iterating star products, and these decoding problems corresponds to the same errors. And it's possible using that to correct more errors than have the minimum distance. And if you look at this decoding problem, at the problem you evaluate, so here, clearly, so you made star product, so and star product is kind of linearization. And if you look at the solutions you look for, they can be interpreted in terms of a short vector in a lattice of polynomial. And the funny thing is that so a lattice of polynomial, which is clearly constructed from the power decoding. And actually, if you look at the dual lattice, short vector in the dual lattice will give you precisely the coefficients of your Sudan polynomial. So directly, I would say I don't know, but using this dual lattice point of view and the point of view of power decoding, we see again this linearization process.
Okay, thanks a lot. I hope this answers the question. Maybe we have time for a last question. So I see we have a question from Christophe, the organizer. So he's welcome to ask his question.
Thank you. Yeah, I mean, actually, it's not so much a question for Alain, because somehow I already asked him, and well, the answer was not that satisfactory, I would say. So that's why I'm asking it again in front of everybody.
I appreciate.
More seriously,
I don't hear you very well.
Oh, no, I should come closer. Yeah, I mean, maybe it's more to start a discussion on Zulip, because I would be really interested in knowing if at some point people have used coding theory to solve problems on curves over finite fields. You know, we have used a lot curves over finite fields to construct good codes, but I'm sure that there are a few articles that have used like tools from coding theory to help doing something on curves. And I mean, if anybody knows references about this, I would be really interested of gathering them. Yeah, that's what I wanted to say. So maybe for tomorrow, that's why I wanted to say it today already.
I'd be interested to, clearly.
I guess so there is a paper by Kaplan last year. I will find the title, but now I can't remember which use read Mueller codes to answer question about plane Kubit's curves. So I will find the title, but now I don't have it on my mind, but must be on Kaplan's page for sure.
I mean, the only one I could say, I mean, it's also something which is related to, I mean, what Everett did at some point, like trying to find the proper way to use code to put the zeros of polynomials in order to like construct hyperelliptic curves with many points and covers one with many points. So this is definitely a way, but apart from this, thanks, Alain.
Okay, I could mention one of my work with Ivan Dursma. Maybe it was the answer, the non-satisfactory answer I gave you last time, but in which we made some, we gave an upper bound on the number of rational points which are in the intersection of a quadric and another, so a quadric in P3 and another surface of degree D, and to get, and we were looking for an upper bound just to get the minimum distance of corresponding codes. And actually it turned out that we finished by obtaining the minimum distance using the BCH bound by observing that we had some cyclic automorphism of the surface. And this BCH bound provides the upper bound on the number of rational points. But this is the only example I have, so should check Nathan Kaplan's paper. Okay.
Okay, thanks a lot. So I guess Christophe is right. It will be a nice topic. Oh, Felipe has another remark. He says that okay, everybody can read it. Okay.
Cool, cool.
Okay.
I can't. Oh, okay. I need to stop sharing.
Okay. So Manin observed that the Hamming bound over F2 shows that the Weil bound is not optimal over F2 for large. Yes.
Nice.
Okay, so as Christophe said, this would be a nice topic for a discussion on the Zulip chat. So thanks again to Alain for his very nice first half of talk, because he will speak again tomorrow.
My pleasure.
So I guess for people in Europe, we resume this evening. Maybe Christophe, you want to say a few words? I don't know. Or...
Yeah, I just wrote it on the chat. Charles' talk is on Friday, so tonight we start at 7 p.m. Paris time.
Okay. Thanks a lot. See you. Bye.
See you.